Hello, calculus students. Today we're going to take a little bit different turn, and we're going to begin looking at numerical methods of integration. Now, it's not true that this is really the complete beginning of that, because I think that you, as we've been beginning to integrate with U substitutions and all of that stuff, you've already seen a couple very basic numerical methods of obtaining the area under a curve. So let's just kind of review the big conceptual place that we're at right now. So I said we obtain exact values for the area under a curve using what? So I think that you should know that to find the exact values of the area under a curve, we use integration. And we have to combine integration, which involves antiderivatives. So we'll say involving antiderivatives. How does it specifically involve antiderivatives? Well, that goes to the fundamental theorem of calculus, right? So this is the fundamental theorem, part 1. Remember, the fundamental theorem of calculus, part 1, says that to obtain the exact value of the integral from a to b, where that means the area under this curve f from a to b, the way you do that is you find the antiderivative of f at b, you subtract the antiderivative of f at a, and that function evaluation becomes the area under the curve. So that's how you find the area under the curve exactly. So I wanted to just remind you that you also knew some numerical methods for finding the area under a curve as well. So what other ways of obtaining approximations for integrals have we already done? So I think you should think back of when we were just trying to find the approximate area and we were using our calculator and those different rectangular approximations. So think about it for a second and see if you can come up with something. Alright, so I think the things that we saw were like left-hand approximations or left-hand Riemann sums with rectangles. We also had right-hand Riemann sums. We also had like midpoint Riemann sums. And we didn't really do any in class, but we discussed the idea of a random point Riemann sum. Okay, so those are the ideas that we had for approximations, and actually also on this list I want to add Math 9. So Math 9, the calculator's integrator, is not doing integrals with the fundamental theorem. The calculator's integral is also an approximation. It's just a very, or I shouldn't say very, but a fairly sophisticated approximation, and so it's really also an approximation. Doing it fundamentally with the fundamental theorem is always a better way to go if you can find the antiderivative. The only problem is sometimes you can't find the antiderivative, and we are not done by any means at learning how to find antiderivatives. We've still got many more processes and specific functions to look at both this year and in Calc BC, where we start to learn more advanced integration techniques. So if that fails, if all those different good things fail, there are other numerical methods you can also use. So that's what we're going to be focusing on today, is these two other numerical methods, which are a little bit more accurate than these basic Riemann approaches up here. And the new methods we're going to investigate are the trapezoid rule, I don't know why I didn't have that underlined, and Simpson's rule. So those are the two topics of this lesson. So besides that, I'd also like to investigate going through an advanced math idea or theory kind of from a textbook. So I'm going to do that. So the trapezoid rule is basically just taking that same idea. Remember when we did like midpoint, left hand, all that kind of thing? So let me get a function on here. So let's say that this is our function curve, okay? Something like this, something real basic. So there's f of x. So when we looked at f of x with like left-hand rectangles, we used this left-hand edge, if that was at A, and we fed it up there and we created a little rectangle. And then we used the next left-hand edge and we fed it up there and we created another little rectangle. Should be connected there. And then we use the next edge and we created another little rectangle. Another way to do that is, instead of using rectangles, to connect this dot with this dot and use a little trapezoid. You can see it's going to be a little bit different. So like then this dot would get connected with this dot and this one with this one. And to use a little trapezoid for each, let me blow one of those trapezoids up. It would look something like this, right? So that's another and a little bit more accurate. You can see that when you do that, usually that's going to provide a little bit more accuracy in your approximation of the function than a simple left-hand edge, right-hand edge, or even a midpoint Riemann sum would provide. So that's what we're going to look at today. So I kind of have the compact series form of the trapezoid rule down here. So this would be if I just like gave it to you and didn't explain where it came from. So today I really also, besides using this to do one problem, I also really want to focus on how to read a textbook and see where something complex like this complex looking series trapezoid rule thing comes from. So before we look at that derivation and textbook stuff, I thought we'd look at a couple problems. Let's just do the same problem and one that we could do analytically as well. Let's use the trapezoid rule and then let's use Simpson's rule to do that problem, okay? So let's have a look. So we're going to use the trapezoid rule, and when you're using the trapezoid rule or Simpson's rule, just like when you're doing a Riemann sum with like the left or the right or the midpoint or whatever, you have to decide how many of the shape you're going to use. So I'm going to use, I think, 4 trapezoids in this first one. So let's do the integral from, let's see, I was going to go from pi over 2 to 3 pi over 2. Just of a nice comfortable function like cosine. So we know analytically that this guy is going to be equal to the negative sine of x evaluated from pi over 2 to 3 pi over 2. So we could do this analytically and we'll see how close the trapezoid rule gets us. We'll see how close that approximation is. So let's actually do this. So the antiderivative of cosine is negative sine, or is it positive sine? The derivative of sine is cosine. So I think it's positive sine. I made a mistake there. There we go. So, alright, so let's evaluate it using the fundamental theorem. We're not even paying attention to this n equals 4 trapezoid business at the beginning. So that's going to be the sine of 3 pi over 2 minus the sine of pi over 2. If I think about 3 pi over 2, that's down here, so that's going to be negative 1. If I think about sine of pi over 2, that's up here, so the y-coordinate there is 1. So I think the exact answer to this problem is negative 2. So now we're going to do it with 4 trapezoids, and then we're also going to do it with Simpson's rule with 4 shapes in just a moment. So let's finish the trapezoidal rule first. So we're going to use the trapezoid rule. Now of course you could add up 4 trapezoids, and in fact on some problems I'd advise doing that, but in this assignment I'd like you to use the condensed series form, which we're going to derive here in a few minutes. So how do you do that? So we know the answer is actually negative 2, so let me get a different color. And we're going to use this. Okay, so first we need to do b minus a over 2n. So b minus a, 3 halves pi minus 1 half pi, that's pi, right? So we're going to say that the integral is approximately pi, because that's b minus a, over 2n. 2 times n is 4 for us, so we're going to have pi over 8. Alright, so I'm going to have pi over 8, and then I have to go the function, this function, evaluated at the left-hand edge. So I'm going to have the cosine evaluated at, you guessed it, a. And I think for this it might be really good to draw what n equals 4 looks like. So let me do that up here. So here's pi over 2. Here's 3 halves. Let's cut that into 4 subintervals. So what's in the middle? That would be pi, right? But that's only 2 subintervals. So if I cut it one more time, I'll have 4 subintervals. So between half and 1 is going to be 3/4. Between 1 and 1.5 is going to be 5/4. Okay, so now my first node here is this one, my second node is this one, my third node, my fourth node, and my fifth node. You can see how this makes use of the first node, the second node, the third node, etc. Okay? So, it says 1 times the first node into the function. Then it says 2 times the second node into the function, so I'm going to go cosine the second node, which is 3/4. Then I've got to go 2 of my next one, which is pi. Then I've got to go 2 of my next one, oops, plug it into the function, which is 5/4. And then you can see the last one here doesn't have a 2, so it's just going to be cosine of that edge. Okay, so now we've just got to do all of those, and we'll have our approximation. So you can see that each one of these is just a unit circle calculation. So cosine of pi over 2 up here is 0, so that's nothing. Plus 2 times the cosine of 3 pi over 4. I think I'll do that here as a little unit circle computation. 3 pi over 4 is 45, 1 square root of 2, negative. So that's going to be 2 and negative 1 over the square root of 2. Okay, so then I'm going to have plus 2 times the cosine of pi. Pi is right here, cosine is x, so that's negative 1. Plus 2 times the cosine of 5 pi over 4. I'm just going to go back to my unit circle. 5 pi over 4 is right here. I think the cosine is going to be the same thing as that 3 pi over 4 one. And then the cosine of 3 pi over 2. 3 pi over 2 is down here. Cosine is nothing again. So you just need to simplify and you've got your estimate. So that's pi over 8. So it's going to be negative 2 over the square root of 2 minus 2. Another negative 2 over the square root of 2. Just keep simplifying. And you'll get, there's 2 of those, right? So there's 2 negative 2's. So really, that's going to be negative 4, isn't it? There's 2 of these. 2 times negative 2 is negative 4 over the square root of 2. Then I've got a minus 2 here. Now you could clean that up by rationalizing and all kinds of stuff. I'm just going to pump it straight in my calculator. So I'm going to do that. I'm not going to show my work this time. I got negative 1.896. So pretty close to negative 2, but not super close. But that was only with 4 trapezoids, mind you, so not a great approximation. Now let's apply Simpson's rule and see if we can refine our estimate. Let me give us some more space here before we do that. Let me get this guy out of the way, in fact. I think I'll just delete it for now. Let's give us a lot more space. Hold on just a moment. I want to get rid of this guy. Come on. There we go. There, now it's nice and out of the way. So you can see Simpson's rule works really similarly. So if we want to do this same one, I think that we're just going to change up how we use our nodes. So let me draw our nodes down here one more time for Simpson's rule, and we'll do it that way. So now we're going to approximate that same integral. We'll still use 4 shapes. Simpson's rule doesn't use trapezoid. Simpson's rule actually uses pieces of parabolas. And that's part of your assignment, is to kind of look at those pieces of parabolas in more detail, like I'm going to for the trapezoid rule here in a moment. I'm going to derive it out of the book, and you're going to go look at the book's derivation for the Simpson's parabola pieces. Anyway, though, you can see that this is really similar, except instead of having a 1, 2, 2, 2, 2, 1, it's going to be 1 and then 4 of the second node, 2 of the next one, then 4 of that third one, 2 of the next one, then 4, then 2, then 4, then 1. Okay, other than that, it's going to work really similarly. So we're going to say the integral is approximately equal to b minus a. For us, remember, b minus a. Let's just remember what we're trying to integrate here. It's going to be pi over 2 to 3 pi over 2 of cosine of x dx. So that's approximately equal to b minus a. Let me get this junk out of the way for you so you can see clearly here. So that's going to be b minus a is going to be 3 halves pi minus 1/2 pi. That's going to be pi over 3n. This time n is 4, so it's going to be 12. And then we're going to go the first node 4 times the second one. We should get our nodes down one more time, right? So we had half pi was the beginning, then 3 halves. In the middle cuts it into 2 pieces, but I wanted 4 pieces, so I'm going to cut it one more time. at 3/4 and 5/4. Okay, so 1 times the first node. That means cosine evaluated at that first edge. Then I'm going to go plus 4 times cosine evaluated at the next node. Then 2 cosine evaluated at the next node. Then 4 cosine evaluated at the next node. And finally, we're going to have cosine evaluated at the last node. Get a nice bracket on that guy, and you've got it. So let's see, that's going to be pi over 12. And I think we just did these unit circle computations a second ago. So really, these 4, 2, 4, 1, 1 is just going to be different weights on the same numbers that we had a second ago. So it's really interesting how these different node methods relate to one another. So cosine of pi over 2 from a second ago, I think turns out to be 0. Then we had 4, and if you remember, cosine of 3 pi over 4 was negative 1 over the square root of 2. Cosine of pi is, of course, negative 1. Cosine of 5 pi over 4 is negative 1 over the square root of 2. And the cosine of 3 pi over 2 is 0. So what's that simplify to? I think it's pi over 12. This is negative 4 over root 2 minus 2 minus 4 over root 2. We can put our like terms together the same way or a different way than last time. So I've got negative 8 roots of 2 minus 2. And then I can stick that in my calculator. So I went ahead and stuck that into my calculator, and this is what I got this time. I got negative 2.0046. So you can see that's much closer to the true answer than negative 1.8 was. And that's because, not because I used a greater number of rectangles, I still have 4 over here. It's because that Simpson's rule is a little bit more accurate than the trapezoid rule, and that's because it's using parabolas to connect shapes. If you think about this theoretically, like let's go back up here to the top like we talked about a second ago. I don't have that picture anymore. It's going to be using parabolas to connect one point to another. Let me try to draw what I mean there real quick. So if you've got a function that looks like this, one way to connect one node to another, like here's x0 and x1, is to use a straight line. But what Simpson's does is it tailors a parabola between this point and this point. And you can see that that's going to hug the curve a lot better, and you won't get all this error like you would for the linear way. Okay, so now let's go look at how to derive the trapezoid rule, just so we can learn a little bit more about how to read an advanced mathematical text and understand it. I'll see you in a moment.